Hello, we are Team 5, and this is Fourier Transform Infrared Spectroscopy.
So hi, this is Merida, and we're going to start off talking about the FTIR device, and here you can see it on the left side. What it does, it acquires infrared spectrum of varying techniques such as absorption, photoconductivity, and emission of different matters such as solid, liquids, and gas. It has a capability of collecting data over a large range. It's fairly expensive. It helps identify compound materials such as plastics, rubbers, adhesive, and paints, and it has 15 times the magnification.
Hi, this is Stephen, and we're going to talk about the technique of how Fourier Transform Infrared Spectroscopy works. So there's two components really. There's a hardware and a software component. The hardware is going to be used by emitting an infrared source of radiation through a beam splitting lens, which is going to reflect onto a sample. It's going to be on the surface of the detector. Inside of the machine are going to be two mirrors. One of them is going to be stationary and at a fixed distance from the beam splitter, and the other can be moved at different distances to increase or decrease the intensity on the sample. Once the light is passed through the sample, the detector will communicate with the software to produce an interferogram, which is going to be the Fourier transform of the original wavelengths that were detected on the sample. And once the Fourier transform happens, the wavelength that would have been here is now the wave number. This Greek letter here, this nu, is the inverse of the wavelength. So any of these peaks tells us about what types of functional groups are present in the sample. As far as resolution, we're talking about 4 inverse centimeters, which if we go back from the Fourier transform to what would be measured here, we're talking in the nanometers.
Hi, this is Ihoma, and these are the data. This is what data looks like for the Fourier transfer. So the Fourier transfer analyzes both organic and non-organic materials, and it identifies the molecular compounds that are found in the sample. So the data is expressed on a graph with the x-axis representing the infrared spectrum. This shows the intensity of the infrared, and it has absorbance bands, which are the peaks. And this shows the vibrations of the sample's atoms, like when it's exposed. On the y-axis is the absorbance or the frequency. So more about the absorbance bands, there are 2 types. There are group frequencies, which these are small groups of atoms, and they're used to tell what functional groups are in the sample. And there are also fingerprint frequencies. These are less reliable for identification, but they help show what's going on in the molecule.
Hello, my name is Marianne. I'll be talking about types of samples for use. So samples we can use would be powder, solids, and liquid. There are several methods that can be done to prepare samples into FTIR. Powder samples is taken with potassium bromide. They're pressed into a pallet, and the pallet is placed onto a rack that will go into a light path to shine the light directly through there. Nigels are oils, and the liquids are mixed with the nigels samples, which are then placed onto 2 solid chloride plates, and the light path is shined through it. If the samples are already thin or can be pressed into thin film, it is then placed into cassettes to be placed into the light path to be analyzed. Attention total reflectance. These samples are placed onto a crystal, then is placed into FTIR and tightened down to be analyzed. For example, when using an animal bone, the specimen is grinded using a grinder at 20 Hz for 20 to 25 seconds. This is done for 3 to 5 times, and specimens can also be grinded with a pestle and mortar. KBR is added to mix the sample, and once the sample is grinded, it is then sieved and put into the device.
Here is a list of our works cited for this project.